Imagine standing completely still while a spaceship hurtles past your line of sight at 80% the speed of light. From your perspective, the clocks inside that ship appear to tick slower. But from the crew's perspective, looking back out at you, your clock is the one running slow. Physicists have wrestled with this precise scenario since the theory of special relativity was first published over a century ago. Reconciling these two seemingly contradictory physical realities is the foundational challenge of modern physics. For generations, students have resolved this paradox using a specific set of equations named after physicist Hendrik Lorentz. Calculating the exact difference in time requires tracking coordinate systems, managing fractions, and deploying the Lorentz factor to balance the math. The numbers work perfectly, but wading through pages of algebra makes it remarkably difficult to actually visualize the physical relationship between space and time. Curious tone. We can actually step back from the massive equations entirely. If we want to fully describe how a moving perspective relates to a stationary one, we only need to look at two specific numbers. The first is velocity, v, expressed as a percentage of light speed. The second is the time dilation factor, determining how much slower the moving clock ticks. If you square both quantities and add them together, the result is exactly 1. Squaring two values to equal 1 is the exact mathematical definition of a point on a unit circle. In this framework, velocity and time dilation are physically locked together as the two components of a single geometric object. We place time vertically and space horizontally. A vertical arrow represents a stationary observer at maximum temporal rate. Accelerating to 80% light speed tilts the arrow right, dropping the temporal component to 0.6. At light speed, the arrow falls flat. Time shrinks to 0. The speed of light acts as a rigid geometric boundary. Because the arrow cannot stretch past a length of 1, traveling at maximum spatial speed physically forces the passage of time to cease passing. With this visual model built, we can answer our original question. How do we calculate the exact difference in time between the moving clock and the stationary one? In geometry, there is a standard operation used to determine how closely two vectors align with each other. It is called the inner product. This diagram illustrates the alignment between the two perspectives. Calculating the inner product is done simply by finding the cosine of the angle nestled between those two arrows. A moment of wonder. By finding that angle, we bypass the pages of algebraic transformations. The geometric alignment between those two arrows literally is the time dilation factor. We traded a complex knot of calculations for a clean visual relationship. We found the hidden geometric skeleton of spacetime. The specific tool we used to solve this was vector alignment, and this single mathematical operation appears far beyond the physics of moving spaceships. If you study quantum mechanics, you map the relationship between two subatomic states using this exact same inner product geometry. If you build large language models, the artificial intelligence calculates the semantic relationship between different words by measuring that exact same geometric alignment. This pattern suggests a concept called resonance. Drastically different systems, whether natural physics or synthetic algorithms, operate under the exact same structural logic. Stripping away the complexity of any one specific field reveals a quieter truth. Across the edges of reality, the universe continually reuses the same elegant geometric architecture.